All right, guys, welcome to ITS 350. Let's get started. So today we have, today's Tuesday, so we have a lecture. I will continue our discussion. We're getting actually a little bit close to ending our discussion of cryptography. If you look at the semester, we really have like 7 weeks left, I think, something like that. So we're going to start wrapping things up today. We're getting close to the final set of lectures on cryptography. We've really covered everything. And if you remember, at the end of at the beginning of the semester, I said, you know, we're going to start with Open SSL. You know, what is Open SSL? And so, you know, if you remember at the beginning of the semester, I said, or what is SSL? Your socket layer. And then I said, well, you know, I'm gonna actually give you this. I'm gonna mute your microphones. So I said at the beginning of the semester, I'm actually going to give you this definition of SSL later in the semester because we have to cover a lot of primitives of crypto primitives, right? We have to cover them, and we have at this point we've covered symmetric and asymmetric encryption. We've gone over, you know, RSA. We've gone over a lot of the algorithms and how everything works. We've talked about the principles and how they relate to cryptography. So we've talked about confidentiality. And we talked about integrity, right? And we've talked about authentication, right? And so we've talked about a lot of these ideas, right, this semester. And so now that we've covered all of this, we are now finally ready to define SSL. Okay, so that's really the last lecture, if you will, on cryptography. And so, but today we're not there yet, but I'm just saying that's where we're heading. Today we still need to cover and finish up blocked ciphers. Okay, so if you remember, we were talking about blocked ciphers and we actually started to talk about the data encryption standard. So my plan for today is to finish this up. Remember, you had a little quiz, short quiz about it, right? And today I'm going to go over that as well. And then after that, you know, that should take us towards the end, towards SSL. Okay, once we've covered SSL, I usually, what I like to do is I like to do a practical, call it exam, I guess. And it's just going to be something, we're going to use a set of Python libraries. It'll be pretty easy. The coding is going to be very easy. I'll give you most of it. And really the idea is that I'm going to ask you, you're going to have to work with a partner, right? So, you know, Bob and Alice. And I'm going to give you a set of problems and exercises that you have to do with the person you work with. And you will have to achieve a lot of these principles and use a lot of the techniques. Okay, so pretty much everything. It will encompass everything that we've done so far this semester. So that will probably be sometime next week. We will start that. And like I said, it'll be a series of practical exams that we will do in the class. And, you know, the idea is to make sure that you guys have a final understanding of how everything else, you know, creating your public-private keys, symmetric keys, and all that. And then we'll wrap up, you know, the cryptography part of this, so the crypto part of 350. All right, and then after that, which is just a basic introduction to cryptography, but hopefully you got a good understanding of that. And then that as it relates to the principles of, the principles, right, of information assurance that we've talked about. But as you might imagine, the principles of information assurance, principles, don't just apply to cryptography. Now that you know how they apply, you know that, they apply to other areas, like they might apply to biometrics, right? And they might apply to other types of security. So that's, we're gonna take a look at those applications. We're also, a big topic that we're gonna introduce is going to be detection systems. And in particular, we will talk about intrusion detection systems and firewalls. And that basically relates to access control. And since among other topics, so malware detection, so a little bit of malware as well. All right, so these are kind of the topics that we will wrap up. So and these also we're going to look at from the point of view of the principles. So principles of information assurance. Which, as you might remember, we had that acronym CIANA, right? So confidentiality, integrity, availability, non-repudiation, authentication. All right, so we will kind of look at that. And finally, at the end of the semester, we're going to cover the risk and control matrix and risk assessment. So this is a topic that is very important. It's not very technical per se. It's more of a procedural kind of a thing, but it's also really important. This will be towards the end of the semester. Okay. Additionally, at this point, it wouldn't be a bad idea for you to start thinking about, since we're getting closer to the end of the semester, it would not be a bad idea to start thinking about your term project. So your term project, if you've looked at the syllabus, is worth 10% of your grade. You can work in groups of 2 or 3, up to 3, no more. And just pick a topic. So pick a topic that you want to explore, right? Related to cryptography, the principles of information assurance. And then you will present it. It's nothing big. It's only worth 10% of your grade, but you will have to do a presentation. And this is going to be the week before finals. So you're going to do a presentation. We're going to do the presentations via Zoom. And you can share your screen while you're doing that. And you're going to do a demo. So the idea is that you're going to either write some code or you're going to find a program, figure out how it works, configure it, and then, something. For instance, you could do like a man in the middle of attack of a certificate authority, right? So you could do something like that. So it's really pretty broad. I'm not very... you could do YouTube videos if you want to do your presentation like that, but you have to be there to answer questions later. But I would prefer everyone just sharing their screens. It's just less work, but it's up to you. You'll have to play the video. I don't know, I guess. We'll see. You'd have to send it via the chat and then we open the link maybe. We'll see. It's okay to use YouTube videos, but I prefer you just share your screen and you definitely have to be there. Okay, so what I would suggest for now is start thinking of topics. You have to run the topic by me, okay? So you can send me an email, just say this is my group, these are the people in my group, this is the topics, 3 topics that we're thinking about. and then I can help you to choose one. Remember, as I said, you have to do a presentation where you explain what you did, and then you have to implement either some code or some program or a configuration, but it's got to be something that you demo, that you actually run something and you show how it works, okay? So definitely, please start thinking about this and just run ideas by me, okay? All right, so as you can see, that's the plan for the rest of the semester. Wrapping up crypto, as you know, in 350, crypto takes a lot of the time, but then after that, we do explore from the perspective of the principles of information assurance, other techniques, and we'll spend some time on a few here and there. Are there any questions?
I don't think so.
No questions. Okay. All right. So if there are no questions, then let's try to go through the material that's missing that I still need to finish here. And so I'm looking at my notes. All right. So I think I left off on block ciphers. Okay, so we're going to go over that. Now, if you remember on Thursday when we met, I gave you some code and you had you're implementing the CBC mode of operation, right? So that's also what we're going to do in lab this Thursday. So I will assign, so that homework will not be due this Thursday, but instead it's like I'm going to assign it Thursday and it'll be due a week from Thursday. Okay, so no homework due this week. All right. I'll help you, of course, on Thursday. My plan is just to kind of, please make progress with the program, but I'll help you out a little bit more just to kind of get it finished up. And then, as I said, I think I can probably finish between today and next Tuesday. I can finish the crypto theory, and then we will be ready for the crypto practical exams. I'll just, the code is already posted, and I'll just give you some examples of how to do it. And then, like I said, the goal there is not coding per se, but it's really about encrypting things correctly. All right. I said I'll give you a set of problems. Anyway, so let's finish up then with the data encryption standard. So I'll just give a brief recap. So the key thing when we're talking about data encryption standard is a block cipher. Block cipher. And the goal is to map n bits to n bits. So you want to map n bits to n bits, and you have associated with that some kind of an encryption and decryption, and you have the idea of a key, and the key is k bits. Okay, so that's the assumption of the algorithm. That's what we have to do. All right. Then I started talking about how the basic idea of DES is the Feistel network. So the basic idea is to build what is called a Feistel network. All right. So now given some functions. So given functions f1 ... to fd, right? These functions map, and we still need to define those functions. These functions map n bits to n bits. All right, so we're mapping n bits to n bits in some scheme. Okay. So we can define this. We can define we can define F1 ... through FD as such. So we can say that we have a mapping like that. All right, so from a block of n bits to a block of n bits. And then we talked about the Feistel network, right? So I gave you guys, so I'll review that as well. We have blocks that are of size 2 times n bits, right? And so we take an initial block, we split it in 2, and then we're going to have a right and a left with index 0. And these are going to be n bits and n bits. So these are n bits and n bits, right? And then we're just going to perform some kind of a, you know, shifting and moving of the data, right? And so the procedure is that basically the right, and then we're going to call this L1 and right 1. Let's say right 0 there. So basically the right 0 simply becomes L1. That's it. It's kind of like it slides down. However, to get R1, we need to do something. We're going to involve an XOR operation that will take L0, and we're going to XOR L0, obviously, well, with right 0. But before we XOR it with right 0, we want to run right 0 through a function F1, okay? So it's like R0 will go in there, right, through that function. And that function is the one we just defined here, so we have to use some kind of scheme. So this function F1 will convert, right, the R0 and then give us a new version. We'll map it to something else of the same size. We XOR these two, and that becomes the input to R1. Then we can take this a step further, right? And then let's call this one R2 and then this L2. So again, R1 just slides down and becomes L2. But to get R2, again, we involve an XOR operation that just takes L1. We run R1 through F2, and then the output of that is XORed with L1, and then that slides and becomes R2. And then we just repeat that process, as you might imagine, until the end. So we're going to end up with, R d minus 1, L d minus 1, and then this over here will give us the final output. So this is the output. This is going to be the input, right? And on here, then this RD LD will allow us to take, again, you know, we slide down RD minus 1 and becomes LD. And then to get RD, we need to XOR LD minus 1. We take RD minus 1, run it through function FD. That XORed those two, and then that becomes RD. All right, and that's, you know, the Feistel network as we discussed it. You know, last week. All right, and that's the assumption there. Now, we can conclude from this that if we want to get Li, right, Li is just going to be R I minus 1, because it's just this one here is just that one. All right, and then once we want to define Ri, which is R1, for instance, that one there, we're just going to know that there's an XOR operation involved. We know that. The element that we take is L0 for R1, so that's like saying Li minus 1, right? And then the other thing is we know that it takes a function f, right? And that function f is going to be fi, right? And then the parameter that it takes as input is going to be r, and it's going to be Ri minus 1. Okay, so that's if you're trying to think about the algorithm itself, this would be the approach to take. All right, so now the question on the quiz was, if you remember, so the quiz last week, you wanted to find the inverse. Okay, so for this one, we drew a slightly different set of letters just to kind of make, force you to think differently. All right, so here we have Ri, Li, right? And we have Ri plus 1, and then we have Li plus 1. And we still know that it's the same logic as before. So it's going to be like that. And then we have an XOR operation involved here. And then again, this. And here we have an fi plus 1 function. So then this becomes that. And then the output of this becomes the input here. So the question was, in that direction, in the inverse, and so now we have the goal is, what is Ri and what is Li? Okay, so the question is Ri and Li. All right, so basically, since I'm going to change color here. To get Li, it's really just, sliding here, right? That's how we get it. So then if we want to get Ri in the same matter, all we need to do is take Li plus 1. Right, so it's basically this one travels now in that direction. Okay. The other one, to get Li, we sort of need the same. We would know from looking at this that obviously it comes from this direction, right? So we know it, this involves an Ri plus 1, right, in some way. And to get that value Li, it means that we're going to XOR this one, right, Ri plus 1. So we already have that one. Okay, and now we need, also we know that we're going to use the function fi plus 1. Okay, so now the question is, usually we would need this and this to obtain that one. Okay, so we already have this one. We need to figure out this one here. Okay, and to figure that one out, basically we know that that value was FI RI, right? RI, but since we don't have RI, we have a problem. We don't have that one. However, we just established that RI is actually LI plus 1, which is something we do have. And so we just have to replace RI with LI plus 1. Okay? And so that's basically the solution to this. So the function we're still going to have, and we're going to have LI, and we just reverse it. And that should be the approach. Are there any questions about this?
I don't have any, at least.
Oh, all right, great. All right, so once we've established that, so we've looked at the what now we need to look at the details of this, in particular these functions, right? So we need to look at these FIs, right? So we still don't know what they are, so we need to define those as well. Okay, so I'm going to switch colors to red. All right, so as we know, F1, comma, dot, 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 F16, right? They're just mapping functions. They map from, let's say, 32 bits to 32 bits. Okay, or 64 bits, or whatever you want to define that to be. So we're going to end up with, 32, 32. Let's say we have 64 bits over here. Okay, this will be the input, and this will go into some kind of Feistel network. All right, and then out will come the, again, same size, 32, 32, 64 bits, and that's going to be the output. Okay, so that's really the idea there. So now let's think about these functions. These functions are a little bit elaborate. So this is, they can have variations. All right, so think of them as something that can be adjusted. Okay, so the function's f. All right, so we're going to say here, we have the blocks that are 32 bits. Okay, let's imagine that that's what we're using, 32-bit blocks. So we're going to have 32 bits blocks. Remember, these are the functions f. So what I'm describing right now is this, right? So it takes 32 bits over here and it outputs 32 bits over there, okay? That's really what's being described right now. So then, if I have 32 bits, what I'm gonna do is, I also will have a key. And the key we're gonna say is actually larger, 48 bits. 48 bits. So what's gonna happen is you're gonna need to extend the 32 bits to 48 bits because they are not the same size, right? So you need to make it bigger. So the way that you can do that is several ways, right? So you know that there's a difference of 16 bits in there. So here you just need to have some approach like padding, or maybe not padding, but something better might be to replicate, shift, right? It's not really going to matter what's beyond that. You're just intentionally making both of these to be the same size. And then once you have that in 48 bits, you're going to perform an XOR operation. I'm going to do an XOR. Right, and that gives you an output, okay?
Professor Calix,
Go ahead, please.
after padding in your circle for the 32 bits, what is that word?
Oh, it says replicate and shift.
Okay, thank you.
And it's just making the like, think about it, like if it's 32 bits, right? We're just adding something here. And it might be just padding, or we just take a little piece from this and move it there, you know, replicate it or copy it, maybe. Does that make sense?
Yeah, thank you.
And the point of it is just to get it to be equal size. It's just, you know, some approach. Let me rewrite these. Replicate or shifting, right? Some approach. All right, and then once you have that, you're going to, so now you have this approach, and now let me just write like an A here. And what I mean by A is I'm just going to continue in the next page. Oops. Yeah. All right, so now I'm going to move to the next page, and I'm going to say A. All right, and then now that continues. This is going to be a block that is 48 bits, as you figure. 48 bits. It has been XORed by the key. All right, and that's, you know, so if you remember the round key, if you had one key, you could create 16 round keys from the original one. So in the Feistel network, every function gets one of the 16 keys. Okay, and then after you've done that, you are going to split sequentially the blocks. So you split them maybe into, so they're all going to be, so it's size 48, right? So we're going to split it into 8 blocks of 6 bits each. And correct my math there, but that should be 48. All right, so I'm going to say 6 bits. And I'm going to say here 6 bits. And I'm going to say here 6 bits. Right, and then dot, dot, dot. And then here is 6 bits. Okay, and so all of these, you can call them S1, S2, S3, S8. In this case, because 6 times 8 should be 48. And now the trick is that the original block, if you remember, was 32 bits. And we said by definition, the function will map 32 bits to 32 bits, right? And so we need to shrink that back to 32 bits. So now we need some kind of a trick to do that. And the way that we can do that is by applying a function, S1, S2, S3, another mapping function, S8. And these mapping functions, these S functions, have a definition. They are basically functions that map bit sequences of size 6 into bit sequences of size 4. Okay, and doing all of this, as it turns out, works. right? So it all works out. So then now you get 4 bits, 4 bits, 4 bits, 4 bits. And then you put all of these together, and that should give you a block that is size 32 bits again, right? Because we know 4 times 8 should be 32. Okay? And so we still need to define these S's, and that's yet another thing we need to define, and something else that could change. But basically the goal is that, so that you can arrive then, because there's always a mapping, right? So you can go in that direction and the same function can be applied to get back the original 6 bits from the 4 bits. So it's always a mapping that's happening, and the operation is usually XOR. And so now we have our 32-bit, we have our 32-bit block. And now we can finally, we're almost done, we can briefly describe these S functions, right? You'll see how they work. The S functions took some research to figure out, but basically the S functions are based on lookup tables. Lookup tables. All right. And you know, a lot of research, you know, let's just say a lot of research went into these, okay, to make sure they seem random and that they would not be breakable and things like that. Remember, this is DES, the data encryption standard, which was cracked in 1997, but still it illustrates how a block cipher algorithm works without the complexity of the more advanced ones like AES. All right. So now the trick is, what are these S are they? So as we said, the S function is defined as a mapping from 6 bits to 4 bits and vice versa. But how are they exactly doing this mapping? And so the idea is that they use lookup tables. So now we can define this one. So we can define it here. And we're gonna do, so here's how it works. So we're gonna, the best way to understand this is with an example. So let's look at an example here. All right, so let's say we have ... there. We have 1100. We have 1101. We have 1110. And then, you know, these tables are big, so they got a lot of information in them. All right. And then over here on here we also have 0001, 1011. All right, so the logic is that this side of the table are called the outer bits. And then on the top over here, these are called the middle 4 bits. So as you might say, if the S function is given a 6-bit value such as 0, 1, 1, 0, 1, 1, that's 6 bits, you know, what would be the output of it in 4-bit notation? So what would be the mapping from 6 bits to 4 bits. All right, so the trick is then, we take this value, so I'm going to take 0, 1, 1, 0, 1, 1. You can see, kind of separating it out a little bit. And so you have the 4 middle bits, which is these, and then you have the 2 outer bits, which are these. So you have to look this up in the table to find the corresponding value. So this table would be populated with numbers. So this would be. All right, so these are that's the table. And so now you just have to find the mapping. So what would be the answer to this one? Which one would you guys select? Right, so somebody said the answer is 1001, this one. And that is correct, right? Because you have the 4 middle ones, they're 1101, there you go. So you've selected that column. And then the 2 outer bits would be 01, which is this one. So therefore, that allows you to select that. And so you perform the mapping over here. And now you get as an answer 1001. And so by doing that, you've done the mapping, okay? And so that completes then, if you look at this over here, the S bit goes from 6 bits back to 4 bits, and going back to the, the Feistel network, you have now completed all of this because you've defined F, right? And you can go, as I said, from 32 to 32 through the function where the F function includes the S functions and so on. And then you go from input to output and you complete the data encryption standard. All right. Does that make sense, guys?
Yeah.
Are there any questions? All right, seems like there's no questions, all right? And that completes or concludes the data encryption standard. So for the homework that we're working on Thursday, I'm not asking you to implement DES. I'm only asking you to implement, the block cipher with a CBC mode of operation. Remember, if you do ECB, you should know why that would be wrong. So that's not the one I want you to do, but only the CBC. So, however, another idea for the term project would be to implement DES or to implement AES. So either implement this one or implement the more advanced one, AES. But I would leave that to you guys. If you do it, though, for this kind of thing, you have to write the code in preferably in Python. All right. Okay. So now that we are done with DES, let's just go a little bit. This is the only algorithm that I'm going to explain in this much detail. And it's really not meant for you to memorize it or anything like that. It's just for you to know, right? You want to know how it works, and now you know. you can see it's nothing more than a whole bunch of XORs, shiftings. There's a fancy lookup table, but that's really all it is, okay? Now, let's go ahead and talk a little bit about triple DES. So historically, I gave you triple DES. We talked about it, right? So if DES is this one, then triple DES would just basically mean what? That you performed DES 3 times. And the idea was that around 1998, you know, they were scrambling to add more complexity because they were able to break DES. And it took, I don't know, 12 hours, let's say. So they said, well, it's taking people 12 hours to break it, or maybe 3 hours, I don't know. How can we slow them down? Well, let's just use DES 3 times. So if it takes 3 hours to break DES with one key, if we use 3 different keys in triple DES, it's going to take them now 9 hours. And that's enough for us to do our encryption and then change the keys all over again, for instance, right? So that's really the intuition there of what happened historically. And so, you know, the idea was, let's artificially expand the keys, the number of keys, or, you know, DES or triple DES as it's called. All right. So one way of defining DES is that you're going to do 3 times E given key 1, key 2, key 3, and of course the plain text message. Okay, so that's really triple DES as it's defined, as you now know. So that's really the idea. But, you know, as you know, this is also slower to encrypt and decrypt. It's slower to break, but also it slows down. So if your movie, your Netflix movie was being downloaded through this, it's just going to take, instead of 2 minutes to start, it's going to take, you know, longer, maybe 6 minutes, right? So certainly not the best. All right, and then after that came the advanced AES, or the advanced, which is, we've talked about this already, so I'm just kind of summarizing. The advanced encryption standard. All right, so the advanced encryption standard, it replaced triple DES because, you know, triple DES was not efficient. Came around 2000, as you know. By a person, you know, by Rigendel, somebody in the Netherlands, I think. All right, this one had bigger key sizes, bigger block sizes. So they basically increased the key size, the block size. You know, there were faster computers at this time, so 128 bits, and key sizes, you know, from 128 bits all the way to, you know, 256. Obviously, as you did in one of your labs, you saw that the bigger the key, the slower your system will be. As I said, AES, I'm not going to get into the specifics of the algorithm. Instead, I leave that as your term project. If you'd like to do that algorithm, you know, that's perfectly fine. But it's similar. There is a little bit of similarity in how everything is, you know, the S functions, those S functions, the lookup tables can be used, and the XOR operations are still there. Okay. And, you know, this performs on a matrix operation level. So So that means they can use some techniques of matrix operations to do things in parallel a little bit more efficiently. All right, so that's pretty much it as far as block ciphers. All right, so that at this time, I would say that concludes our discussion, at least in this class, this semester, for symmetric key encryption techniques. Right? Are there any questions about that?
I don't think so.
All right, so given that there are no questions, right, so all that remains from this is finishing up the Python script that we started last Thursday, right? So we need to finish that up. We'll need to work on that one. For CBC. Okay, so we'll do that on Thursday then, finishing up that lab. Okay. And now, if I'm not mistaken, I think I've covered RSA, all that I needed to cover from it. And so that means that at this time, we are ready to kind of cover the last, as I said, the last conclusion of this. Okay, so now we've looked at all the primitives, and we're just going to bring everything together to present SSL. Okay. All right, and then, as I said, what we're going to do next week is we're going to go over the PyCrypto lab. So you can see that module. I've already loaded it on Blackboard. And so that, that kind of works out really well because today we're finishing up the lectures. Thursday, we're finishing up the code of CBC. And then next Tuesday, I will give you the PyCrypto. So we're going to start with that library. I'll do some examples. And then, like I said, although we're using Python, it's not really a Python coding thing. The code is very easy. It's more about, working with your partner. And although I think, so I'll say this. Usually students, when I talk to them, they think that they understand everything. They're like, yeah, I get it. It all makes sense. And then when we do this, and they understand it if they're always Bob and Alice. So they're always on the same computer and they have all the keys there and things just kind of work. But I've noticed that whenever I ask students to now work with a partner and, and exchange everything via email and satisfy all the principles, they don't understand things. They get confused about which key to use. And so anyway, that may not be the case with you guys, but that's the reason why I do that lab. I take it as a practical exam in a way. And so you'll see that in the PyCrypto lab, I believe I have several problems there, and you will have to solve them. And what I want you to understand about this lab is that it's a little bit complicated for me to do this lab right now because of this whole COVID thing and soon, because usually what you do with that lab, the PyCrypto lab, is you demo. It's a demo type of a lab. So that means that I sit with you and your partner. Usually what happens is that some students finish first and others are still working on things. So it actually works out perfectly that way. Whoever finishes first, I can start with them. They demo, and they need to show me everything. So this is where I need to say, all right, send your friend confidentiality. you need to prove that very well. Exchange the key correctly. Do a digital signature. Do this, do that. All right, and so so we have to do it still that way. So what I think we're gonna do next week is on Tuesday, I will just kind of go over PyCrypto, do some crypto examples. We're gonna do some coding that day. And then on Thursday, I'm gonna give you guys time, but as soon as you have things, you can start demoing. And I'll just make notes. I'll have a notebook or something where I take until we finish, okay? So that may take about 2 weeks. So it'll take all of next week and probably the following, where you guys, some of you are working on it while others can demo. And we're gonna have to do it via Zoom like this. You'll have to share your screen. But that's what we have to do, so that's what we have to do. Does that make sense, guys?
There's a question in the chat.
There is a question in the chat. Okay. Let's see what the question is. Yeah, this will only be for the PyCrypto. The one that you're doing now, the XOR CBC lab, that's just a regular lab you submitted. But the PyCrypto lab, as I said, I use it as a practical exam. So I sit with you, and then you guys demo, okay? Because it's the only way. Sometimes in your lab reports, it's difficult for me to know, right? You know, it's difficult for me to know. And so how much help you had, you know, things like that. So with this one, I make sure that, think of it as you're graduating from your crypto sequence. And so you'll show me, you'll have to demo. All right, as I said, you can start reading through the PyCrypto. Everything should be there, including the problems, although I can make up problems as I go. There's also another exam that we need to do, which is, like I said, I always like to do an exam where I hide a secret message. And I can have multiple secret messages, and I can give you multiple keys, right? And so for you to get an A on that exam, you have to tell me what that secret was. But I have encrypted it in several ways. Do you see that, guys? So you're going to have, you know, the PyCrypto lab exam plus another exam. Both of these are practical exams. Let's call it the Find the Secret or Scavenger Hunt practical exam. So they're just labs. I mean, they're worth the same points as a lab, but you know, they're meant to be fun. They should be fun. So hopefully you. And we'll start doing those, as I said, next. I'll start giving you the code and everything next next Tuesday. It'll probably take a couple of weeks to get through those. Just to clarify one more time, no lab due on Thursday. There is no lab due on Thursday. I'm going to assist a little bit on the XOR lab, but I want to see you guys show something. It's very difficult through this Zoom thing for me to, you know, usually in the classroom, I can just look over your shoulder and I know what's going on. But you need to show me a little bit. As I said, with XOR, I'm not so concerned because it involves coding, and this is not a coding class, although you should know how to do it. I'm not evaluating that. But the PyCrypto and the practical exam, even though they're Python code, they're not algorithms. They are just about using libraries as we have done before. So I do expect you guys to be pretty good at doing that. If you want to read ahead on the PyCrypto lab, you can. You can go to chapters 21, section 21.6 of your book. And also you can go to chapters 23.7. Yeah, section, no, sorry. No, yeah, 23.7 of your book. Both of those relate to the cryptography APIs, which you probably know what an API is. All right, and so we will be using those types of tools to do encryption. So definitely before Tuesday, I would strongly recommend that you read those sections. Okay. Programming, using public key cryptography APIs. Remember, we will be evaluating, digital signatures, RSA encryption, asymmetric, symmetric, all the principles, confidentiality, availability, integrity, non-repudiation, and authentication. All right, so you need to make sure that the only thing I will not make you do is a certificate authority. Instead, we're just going to do digital signatures, but PKI-A already took care of that, so I'm not so concerned about it. One thing I will not, so I should stress, one thing I will not cover in this class is blockchains or Bitcoin or anything like that. Sometimes I get questions about that. However, we do have a graduate level class. So when you're a grad student, probably, if you have an interest in this, you can take that course. And I think it's a grad level course or a senior level at least. And it's the whole blockchain and Bitcoin. That's more, it involves economics and things like that. And so it's not part of this class, but so it's not part of this class, but you can definitely consider that one if you would like. All right, so so that basically, review those sections, 23.7 for public key cryptography APIs and 21.6, okay? And try to, Jane, do you have a question? I can see that you're in the session. Professor Liu? Okay, I don't know. All right, so that's the conclusion. So remember, next week the Pike Crypto Lab is what we are beginning. Are there any questions about that?
I don't think so.
All right, great. All right, so if there are no questions, we've talked about what's coming up. You know what to read. You know what to look for in the Brightspace. Now the last thing that we're going to cover, because we are finally ready to do this, is we are going to cover SSL. Okay, so we're going to cover SSL and just take a look at all the details. Okay, so I'm going to go back to the whiteboard. All right, and in fact, there are two things. So so if you remember, I had done this thing, right, where we were like building this pyramid of blocks, right, and we were building the different primitives, right, and so it's now like we have all the components, and now we can, plug in SSL, right? So we can plug in at the top SSL because we have now all the primitives. SSL, you sometimes will also see SSL or TLS. And you might think that TLS must be a more advanced version of SSL. It is not, okay? These are all, SSL is built on top of a whole bunch of different blocks, okay? Different primitives of cryptography. And so it's really not so much an algorithm, it is more of a framework, okay? So SSL is more of a framework, as you will see today. TLS is a protocol. So what that means is that TLS uses SSL, but it's now, you guys, when you took probably your 170, I want to say, you learned something called the OSI model, correct?
Yeah.
Right. So you remember the OSI model, it had all these layers, right? The IP layer, Ethernet layer, TCP, let's say, or UDP or ICMP, right? Depending on what you're doing. And then you know that you went all the way probably to the application layer. Well, what happens is programs and applications need to be encrypted. It's a necessity. So they invented a block called the TLS. Oops. They invented a block called the TLS layer. But it's simply, it's a whole bunch of functions and libraries in C and C++, and those functions and libraries use the SSL framework that we are about to discuss right now. When we take, when you guys take ITS 454, we will talk about VPNs, which are virtual private networks, which are communications, secure networks through insecure channels, and then we will see that that needs to be encrypted, and we're going to use for that we're going to look at C++, and we're going to use TLS to achieve it. Okay, so when you get to that class, we will retouch on this, but as far as this course is concerned, because it's more about the underlying background, we will only go as far as SSL. Okay, so I always get this question about the difference, so now I kind of just talk about it in the beginning. All right, are there any questions about that, guys?
No.
No questions? Okay. All right, so since we are ready, we can go ahead and get started with SSL. All right, so let me move to a new page. So SSL is the secure socket layer. It could also be a protocol if you want to think of it that way, but it's really, TLS is really the way to think of a protocol. I would just call this a framework. So in general, what we have is, with SSL, we have Bob, we have Alice. All right, let's say we go back to the same traditional problem, right? We have a client-server architecture. So this is supposed to be a laptop. Okay. And then over here we have a laptop in particular through the browser. Okay. And then over here we have a server, and we want to connect to it. Right? We want to connect to our server over here. And so we are going to need to make this communication work, use SSL. So nothing new will be discussed here. Instead, we're just going to bring everything that we know, all the building blocks, right? All of these, right, to put together the framework. And that will really, theoretically, in terms of the theory, this will conclude our discussion of crypto for this semester. And then you just have your practicals. All right, so let's go ahead then. So as you know, there's going to be a certificate authority involved, right? So the certificate authority is still there, VeriSign. Okay. And so the certificate authority will help us to identify who is at both ends of the transaction. So in short, this is how it works. Okay, so let's think about it with an example. A browser requests a secure page. A secure page. Usually this is going to be achieved through HTTPS. Right, so we're going to use HTTPS there. When the browser makes the request, so it kind of goes like that, right? A request to the server. Then the web server sends it's going to send its public key. Okay, public key with its certificate. with its certificate. Number 3, the browser then checks. So the browser then will check that the certificate was issued by a trusted party. So the browser checks that the certificate was issued by a trusted party. In this case, let's say VeriSign. Remember that they will have that information in their browser, right? The private key, the public key, right, of VeriSign, so that anything signed by VeriSign with their private key can be authenticated with the public key. And remember that there's going to be a hash involved there as well. It also checks that the certificate is still valid. So it checks that the certificate is still valid. And that the certificate is related to the site that you contact. So it's going to check all the parameters. After that, after everything checks out, the browser then, after everything checks out, the browser uses the server's public key to encrypt. Okay? What do they encrypt? They encrypt a random symmetric key. To encrypt a random symmetric key. Remember, a block cipher type of a key. Let me just put here in a comment, let's say a DAS, AES type of a key, okay? And it sends it encrypted to the server and sends it to the server. So you can see that here, after everything checks out, the browser uses the server's public key to encrypt a random symmetric key and sends it back to the server. Okay? And sends it to the server. All right, and it might send some metadata as well, but it's all encrypted with that public key. Then the web server, so number 5, the web server decrypts. So the web server decrypts is there a question there? All right, so now the web server does what? The web server decrypts the symmetric key, right? Using what? Using what?
Their private key.
Their private key, right? It's private key. It's private key. Very good. All right. And after that, what do? Now you have the symmetric key. It's currently decrypted. And now what do? Now the server uses the symmetric key to send the data. Now keep in mind here that something can happen. And let me do a little graph here. So I have the client and the server, right? And let's assume that now I have the symmetric key, right, that I'm going to send. So I have the symmetric, and then I'm going to encrypt it with the server pub. Who is Alice, guys? Who are we? Do we have somebody that should not be in this? What's going on?
How many people do we
Yeah.
have in the class?
Going to remove him. I don't know who that is, but there's 25 people in the class. That's not. It's not Alicia. I can see Alicia's there. Something weird's going on. Yeah, I noticed that. I already removed that person, that Alice. And I saw also another strange behavior, but I didn't think much of it. Yeah, exactly. The person that logged in is, I thought it was, I didn't think that it, I thought it was her, Professor Lowe, but it wasn't. That person is gone too.
Yeah, it's probably the same person. They changed their name to Alice, probably.
If you see anyone that you don't recognize, let me know, okay? And we'll just kick them out because they could do something inappropriate or something. So, all right.
All right, yeah, sounds good. Is 25 our normal max?
I think it's not actually. It seems very high. I think we're at like at 23, 24, but I don't recognize any strange names. Like I know all these names.
Yeah, I never really paid attention to the count before, so.
Yeah, me neither. Not really. Okay, so yeah, all right. So I looked at the names. I didn't see anything, but if we keep seeing strange things, they can't share the screen because I have that blocked, but they can write things in the chat. So if you see anything, just let me know, okay? All right. So where was I? Oh yeah, so we're talking about SSL, and we were talking about Bob and Alice. All right. What was I saying? Oh, so I was trying to say that you have the server's pub, right? And you can, because they sent you, and now you can encrypt, and they will decrypt. But keep in mind that you could actually also take some data, encrypt it with this symmetric key. That's something we've never really thought about, and send that as well. So you can send the data, encrypt it, and you can send the key, encrypt it with the pub. When the server gets both of them, what are they going to do? Well, they'll use their private to get this symmetric key, and the second they have this symmetric key, they can apply it to the data and decrypt it. So it works in a way that you can send the data and not have to wait to send the key and then get a response and then send data. Does that make sense, guys?
Yeah.
So that's really something that we can, that can be done as well in the protocol to speed things up. All right, so then, as I said, now the server uses the symmetric key to send the data back to the client, but also here the web server decrypts the symmetric key using it. So hold on, no, see it here. After everything checks out, the browser uses server's public key to encrypt a random symmetric key and sends it to the server. They can also send data. And also, as I just described in this slide, okay? All right, so, and then that's pretty much it. After that, the web server sends back the requested HTML document and HTTP data in encrypted fashion with the symmetric key. So at this point, the symmetric key has been established, so they can both use it together. Right, because the key has been established. So maybe I should conclude in number 7. Finally, they can both send data using the symmetric key. All right. And that's it. And it's done. Now, this can last a minute. This can last 2 minutes. Maybe after 2 minutes, a protocol like TLS would say, okay, time to exchange a new key. And you use another key. And that's just part of the process. They'll do the same, exchange again, and just reestablish the symmetric keys. All of that is usually handled by TLS. So that's what TLS is really good for. Okay. And so that's pretty much it. Everything else. So some just conclusions or reminders. Remember that you have to trust the certificate authority, such as VeriSign. Everything relies on that. The symmetric algorithm is much, and this you did in one of the labs, the symmetric algorithm is much, much faster in doing its job than the asymmetric. So, AES block cipher is much better or faster than RSA asymmetric. Remember, you never transmit your private key to anybody. That's something, don't make that mistake on the practical exam. Okay, if you make that mistake, I mean, that's like, F automatically, right? So you should never do that. The symmetric key is also chosen randomly, as you have seen. And you can change this, every 2 minutes or at least every transaction, it's always going to be a different key. It's not going to be the same key because they can always just exchange new ones. And again, that's what TLS is for, okay? I hope that makes sense. All right, so that concludes, and by the way, you know, one thing I want to say about this is all what I just described today with SSL, all of this that I just described should not have been new to you, okay? My point is that by now, a lot of this should have been repetitive and a summary because you really should understand it, okay?
Yeah, it was just kind of like a combination of stuff that we've already
Exactly, it's
covered.
just binding everything together to finally get the big picture. As I said, if I had said all of this at the beginning of the semester, you would have been confused, right? You know, what is he talking about? Authentication and this and that. But now you understand everything. And so now it makes more sense. Okay, what is SSL? And so that's why we have to take that approach of looking at the primitives first. Okay? All right, so I just, I said, I'm done. So believe it or not, this is the end of the discussion of primitives or ideas or concepts of cryptography. Everything else that we have left in the next 2 weeks is just practical exams that we will be doing. So just be ready for that. A lot of demos. The last, and I just have a few loose ends, so I really want to just make sure I've covered everything. So if I do anything else, it might just be like doing another RSA problem, okay? I feel that I do want to, you're obviously going to get in the next exam, in the next second exam, which will be on week 12. I think currently we are on week 9. So in about 9, 10, 11, so in 3 weeks or so, you'll have a second exam. You can expect another RSA problem. Obviously this one, where you have to calculate P and Q and all that, will be a little bit harder. Okay, and the other thing is, I'll talk a little bit about factorization, and that's just how RSA relies entirely on the security of N. That, you know, the idea that getting N from P and Q is very easy, but if you have N, getting P or Q is really a hard problem. Okay, and so that's something that I'll talk a little bit more about, but I think I'm just going to save one lecture where I do a few last problems. All right? All right, so that's all I have for today. So I'm going to stop the recording right now. Oops. All right, so I'm gonna stop the recording right now and just leave it open to questions if you have any questions. Otherwise, we can stop here for today, and I will see you guys on Thursday. So just if you have any questions, stay over. Otherwise, you know, we'll meet on Thursday.